Today we are going to explore electrical wiring. First, what is the most commonly used material in electrical wiring? The answer to that is copper. Actually, aluminum is the other material that can be used in electrical wiring. Aluminum wire was common in North American residential wiring from the late 1960s to the mid-1970s due to the rising cost of copper. And nowadays, aluminum conductors are still used for bulk power distribution and large feeder currents because they cost less than copper wire and weigh less, especially in the large sizes needed for heavy current loads. However, aluminum's tendency to cold flow under pressure and to form an insulating oxide layer on the surface determines that it can't fundamentally be a better option than copper in electrical wiring. So why copper? There's a list of beneficial properties copper possesses, such as high electric hull conductivity, tensile strength, ductility, creep resistance, corrosion resistance, thermal conductivity, and the list goes on. So basically, materials with more beneficial properties than copper aren't cheap, while materials cheaper than copper don't have much beneficial properties. That's why copper is a dominant material used in electrical wiring. Then, besides material, what are the other factors affecting the energy efficiency in electrical wiring? First, let's see the experiment we've done to find out what determines the resistance of a material.
Alright, so if you look at the circuit, we got a voltage meter, we got 30 centimeter wire, it's made out of copper, and the cross-sectional area is 22 gauge. And there's a 6 voltage battery. Now let's see how the current looks like if we complete the circuit. If you look at the ampere, the current, it's around 4.8-ish ampere. So now we change the wire. It's the same length of 30 centimeter. It's made out of copper also, but the cross-sectional area is different. It's 12 gauge. So this one is the thicker one. According to our theory, according to our equation, bigger the cross-sectional area, it should give us less resistance. Thus, we should get a larger current because our voltage is fixed and the resistance is smaller now. Now let's look at the results. Check this out. Now we see a current of around 6 ampere. Now that tells us that having the same material and the length, the cross-sectional area is inversely related to the resistance. Throughout this experiment it was shown.
As shown in the experiment, the equation for resistance of a uniform specimen of the material is the resistance is equal to rho times the length of the wire divided by the cross-sectional area of it, which demonstrates that the resistance is inversely proportional to cross-sectional area. In order to achieve greater efficiency, people want to minimize the heat loss, which is the primary energy loss in electrical wiring. So the power is equal to the voltage multiplied by the current. According to Ohm's law, the voltage is equal to resistance multiplied by current. Hence, heat loss is equal to current squared multiplied by resistance. Transformer designers cannot change the current or the current portion of the I squared times R losses, which are defined by the load requirements. They can only change the resistance or R part of the I squared multiplied by R by using a material that has a larger cross-sectional area to reduce the resistance. So, using proper material with large cross-sectional area to maximize the energy efficiency is why huge